Hello, this is my third lecture, and in second lecture we have discussed about the equipotential surfaces. What are equipotential surfaces? The surfaces that contains equal potential at all their points are called equipotential surfaces. The characteristics we have discussed about the equipotential surfaces are these: that at every 2 point of an equipotential surface, the potential is constant, means the potential difference between any 2 points on equipotential surface is zero, means work done in displacing any charge particle from one point to another point in an electric field on an equipotential surface is always equal to zero. The next character is the electric line of forces are always perpendicular to the equipotential surface, because we know that the work done in displacing any charge particle on equipotential surface is zero, and it is only possible when F and dr, means displacement of charge particle and force on charge particle, are perpendicular. So electric line of forces that shows the direction of force on charge particle and displacement on equipotential surface are perpendicular. So electric line of forces are always perpendicular to the equipotential surface. Next, no two equipotential surfaces crosses each other just like electric line of forces, and the reason is similar. The equipotential surfaces never cross each other. This we have discussed. Now we are going to do the questions based on the equipotential surface. The different cases in equipotential surface. One more point I want to discuss with you, that is, we know that del W is equal to, or dW is equal to F dot dr, and I also know that dW is equal to F dr cos 180, or dW is equal to Q0E. E is electric field intensity and Q0 is the test charge particle dr, and cos 180 has the value -1. So dW upon Q0 is equal to minus E dr, and dW upon Q0 will be is equal to changing potential. dV is equal to minus E dr, or E is equal to minus dV upon dr. So E is inversely proportional to dr, means in a strong electric field the spacing between the equipotential surfaces will be smaller, means where the electric field intensity is greater, then the separation between the equipotential surfaces will be smaller. Understand? So electric field intensity is the differentiation of potential with respect to position. So with this respect, we know that, and when the electric field intensity increases, the separation of equipotential surfaces becomes smaller and smaller. So with the help of these characteristics and definitions, we shall discuss about some important questions based on equipotential surfaces. The first question is, which I have selected for you, is that the question is that draw equipotential potential surface for plus Q charge or minus Q charge. For plus Q charge, the equipotential surfaces for a pointed plus Q charge, this is pointed plus Q charge, then equipotential surfaces as the closer the charges, electric field intensities the concentric circles are there, and the direction of electric field intensities is similarly for negative charge. Equipotential surfaces are just like this. So these are the equipotential surfaces in the shape of concentric circles, and at strong electric fields the spacing is smaller, and at the weak electric fields the smaller will be greater. This is the first question. Draw equipotential surface for plus Q charge or minus Q charge. The next question is that we draw the equipotential surfaces for the group of two charges, and the three cases are there in these cases when two positive charges are placed very close to one another, and when two negative charges are placed very close to one another, and when equal and opposite charges are placed very close to one another, means electric dipole. So we draw the equipotential surfaces for these three cases. The second question is this one. The second part or second question, draw equipotential surfaces for two charges placed very close to one another. And there are three cases in this condition. Two positive charges placed very close to one another, two negative charges placed very close to one another, and two equal and opposite charges are placed very close to one another. The first one is two positive charges are placed very close to one another. We know that the electric line of force pattern are this, just like this. This is the pattern of electric line of forces, and equipotential surfaces are these. This is the pattern for equipotential surfaces when two positive charges are placed close to one another. And for the second case, when two negative charges are placed close to one another, then in that case we consider two negative charges and their pattern of electric line of forces will be similar, but the directions are different and moving towards the charges. As we are aware about electric line of forces, this is the pattern when two negative charges are placed very close to one another, and electric line equipotential surfaces have the shapes just like that. This is the shape when two negative charges are placed very close to one another. And the last is plus Q and minus Q. A positive charge and negative charges are placed very close to one another, then the pattern of electric line of forces for an electric dipole is just like this. And this is the pattern of electric line of forces for an electric dipole, and for equipotential surfaces it is the again concentric circles. And this is the plane where potential is 0. V is equal to 0. This plane is in this shape, and this is the value is 0. So here is V is equal to 0, and this is the plane of zero potential, and these are the two equipotential surfaces when two equal and opposite charges are placed very close to one another. So these are the pattern of equipotential surfaces, and these are the frequently asked in the board examination. The first pattern, when positive charges are there, the pattern is just like this. When negative charges, the pattern is same, but the direction of electric line of forces are different. And for a electric dipole, or when two equal and opposite charges are placed very close to one another, then the pattern will be just like this. Now we shall discuss about the third case of we draw the equipotential surfaces for a uniform electric field. For uniform electric field, we draw the another equipotential surfaces just like this. Draw equipotential surfaces for uniform electric field. Electric field. Draw equipotential surfaces for uniform electric field, and we know that for a uniform electric field, the electric line of forces are always parallel to one another. The equipotential surfaces are also parallel to one another, and also spacing between them is also remains same. So this is the pattern of equipotential surface for the case of uniform electric field. If the direction of electric field remains same, but the magnitude of electric field intensity increases gradually, then in this case, when the electric field intensity increases, the space separation of equipotential surface decreases. If for the case when the direction of electric field remains the same, but magnitude gradually increases with the distance, then direction remains the same, but magnitude increases. Then in this case, the equipotential surfaces, just like that, we can see that along x-axis the direction is same, but equipotential surfaces, this is the direction x-axis, this is z-axis, this is y-axis, and this is z-axis. Then equipotential surfaces are just like this. As the electric field intensity increases, the separation of equipotential surfaces continuously decreases. The spacing between the equipotential surfaces decreases. This is like this distance is x1, this is x2, this is x3, then x1 is greater than x2 and x2 is greater than x3, means spacing between the equipotential surfaces continuously decreases. So if the magnitude direction remains constant and magnitude gradually increases, then the spacing between the equipotential surfaces continuously decreases. And if magnitude of electric field intensity decreases, then spacing will be increases. And for the case of a grid, when a grid of charge lines is placed, then initially the shape of the surface or the equipotential surface is curved, but as the separation or distance increases, the equipotential surfaces becomes planar to one another. For a grid, charged grid, curve equipotential surfaces are obtained and at far distances equipotential surfaces becomes plane. So this is all about, and we have discussed some important questions. Some of are from the NCERT book and some are frequently asked in board examination.